Good afternoon and welcome to today's Society of Fire Protection Engineers webinar entitled Application of Fire Detection Technologies in Today's Data Center and Communications Infrastructure. My name is Morgan Hurley and I'm the Technical Director of the Society of Fire Protection Engineers. Today's webinar is sponsored by Xtralis. Before we begin, let me explain how you can participate in today's presentation. First of all, if you have any technical difficulties during today's sessions, simply hit F5 to refresh your webinar console. If you need assistance solving computer issues, please click on the yellow Help button below the slides. You may also download the slides by clicking the green folder icon at the bottom of your screen. We welcome your questions during today's event. Just type your question into the question window on the side of your screen and then hit the Submit button. We will answer as many questions as we can during the Q&A session that will follow the main presentation, but please feel free to send in your questions at any time. Please also be aware that today's session is being recorded and will be available on the Fire Protection Engineering Magazine website within the next week. You'll be notified by email when the archive is available. The Society of Fire Protection Engineers will provide current SFPE members 0.1 continuing education units for participating in today's live webinar in its entirety. Certificates will be sent by email next week. Now, let me introduce today's presenter. Stephen Joseph has spent the last 11 years of his 21-year career in fire protection focused on deployment of detection technology, more notably air sampling type systems. Throughout his career, he has held various positions with duties and responsibilities that have taken him across a vast range of industry segments, gaining him exposure of the fire risks and challenges associated with each. Along with his electrical engineering, marketing, and business management background, this exposure has allowed Stephen the opportunity to uniquely address fire detection needs of industry, which has included leading corporations across North America, ranging from telecommunications, semiconductor, power generation, to oil and gas. Stephen has participated with code development committees over the years and is active in various industry associations and organizations, such as National Fire Protection Association and the Society of Fire Protection Engineers. Stephen serves as Director of Industry Development for Xtralis, the leading manufacturer of VESTA air sampling smoke detection systems. With that, Steve, the floor is yours.
Great. Thank you, Morgan. Thanks for the introduction. And welcome, everybody. Thanks for joining in. All right. So our presentation today is part of an education series on the application of fire detection technologies for facilities housing IT and communication infrastructure. All right. So just as kind of a recap here, in Part 1, we introduced fire risks and associated consequences, detection objectives and challenges, types of detection technologies, and selection criteria with emphasis on application of aspirating smoke detection. In summary, disruption to the function of IT and communication centers is costly. Reliability must be ensured. Smoke from either an external or internal event can have tremendous consequences on the reliability and uptime of the network. So automatic fire detection systems play an essential role in the overall fire protection strategy, providing first line of defense against fire, that being thermal, or smoke being non-thermal threats, early intervention by personnel to mitigate potential incidents, potentially mitigates the need for fire department response, initiation of sequential systems or procedures such as fan shutdown, suppression release, transfer of data, and so forth. And given the dynamic environmental and operational characteristics of mission-critical facilities, meeting detection objectives can be challenging. So consider factors such as magnitude and direction of airflow, the circulation modes of temperature, equipment cabinet layout, concealed and enclosed spaces, and overall room geometry. All right. So technology innovations and business needs have outpaced prescriptive measures, leaving to question placement, spacing, and selection of suitable smoke detection technologies. The result is a shift towards performance-based design, which assesses applications according to specific environmental and operational conditions to meet particular facility requirements and owner objectives. The performance-based design approach is widely used and is employed to justify designs not covered by codes or where an improved level of fire protection is required. Examples of specific guidelines for the use of performance-based design and risk management concepts are addressed in codes and standards such as NFPA 75, the standard for protection of electronic computer data processing equipment, and NFPA 76, recommended practice for the fire protection of telecommunication facilities, BS 6266, which is the code of practice for fire protection for electronic equipment installation, and Australia New Zealand 4360 risk management standard, and of course the SFP Handbook of Fire Protection Engineering. So due to the nature of their function, aspirating smoke detection technologies lend themselves effectively to performance-based design and have been widely adopted as the most suitable detection technology meeting performance objectives of modern IT and communication facilities worldwide. So as a recap for those who may have missed part one, a typical aspirating smoke detector consists of sections of small diameter pipes with sampling holes drilled at regular intervals along the lengths. And an aspirating fan in the detection unit at one end of these pipes actively draws in air and smoke through the sampling holes towards the detection chamber, which is housed in the detection unit. So once inside the detection chamber, a laser light scattering technique is used to determine the amount of smoke present in the air sample. So a properly designed and commissioned aspirating smoke detection system overcomes the challenges of dynamic environments meeting performance objectives by the nature of their operation. Advanced aspirating smoke detectors detects fires at their incipient stage, allowing early intervention for investigation and action, potentially before smoke and corrosive gases affect equipment and personnel. Can overcome the effects of dilution by cumulatively sampling aggregation of smoke being actively drawn in by multiple sampling holes. Can monitor all stages of fire development from incipient to fully developed, providing multiple alarm thresholds for staged response. Are virtually unaffected by magnitude and direction of airflow or by temperature extremes. Where a gaseous or sprinkler fire suppression system forms part of the overall fire protection solution, FM-approved aspirating smoke detection systems can be designed to actuate release mechanisms. Some systems can provide analytic information about the environment. They can be mounted in easily accessible areas. This allows for easy and safe system maintenance when sampling in concealed locations such as below raised floors, underground cable vaults, and will not disrupt operations and maintenance will not cause security breaches of secure spaces. And of utmost importance, they can provide absolute fixed sensitivity requiring no calibration throughout the duration of their operation. That's just really a recap of, again, those of you that missed part one on air sampling detection technologies. So in part two, while we covered, in part one we covered the what and why, in part two we're going to cover very specifically the how. So with so much at stake, aspirating smoke detection systems must be effectively applied, regardless of how superior or fit for purpose a detection technology may be. If not applied appropriately, or for that matter applied at all where warranted, fire safety objectives may be compromised. So part two will focus on specific application guidelines and leading edge practices with respect to application of aspirating smoke detection technologies, which set out to ensure maximum and most effective level of protection. We'll discuss design considerations, coverage techniques, equipment selection, coverage areas, and integration to other systems. So before designing a system, consideration must be given to coverage objectives. It's essential to gather information about which areas are to be protected and a level of performance for each area. This requires that we understand both fire risks and significance each area serves so that we can determine what level of protection is required in terms of density and sensitivity of detection points, or in our case, sampling holes, to achieve the desired response. Bear with me here. So before designing a system, we got to collect information about which areas are being protected. We talked about that in terms of what level of performance. And so as we consider that more specifically here, we got to take into consideration the assessing the criticality, and that is what significant function does the area serve in terms of the overall mission of the operation. Hazard level, that is what hazards are present, such as combustibles, heat loads, and so forth. Of course, the value of the assets housed within the area. What exposures are there from adjacencies? Will a gaseous or sprinkler fire suppression system form part of the overall fire protection solution? And if so, will detection be required? And what are the project requirements and owner expectations? So assessment of the risks and performance requirements specific to particular areas within IT communication facilities forms the basis for the level of protection applied in terms of sample point density and nominal sensitivity, as we discussed. So in Part 1, we introduced 3 acronyms referenced in performance codes such as NFPA 76 and industry practices. And those were more specifically SFD, which refers to standard fire detection with spacing at 900 square foot and alarm sensitivities typically at that stated by the device's listing. But generally, we'll find around 2.5% obscuration per foot. Then we have the category of early warning fire detection with spacing at 400 square foot and alarm sensitivity at 1.5% obscuration per foot, as referenced in NFPA 76. And the reference to VEWFD, very early warning fire detection, considers spacing at 200 square foot and alarm sensitivities at 1% obscuration per foot at the sampling point, as referenced in NFPA 76. So increasing placement density and sensitivity improves the chance of detecting incipient low-energy fires, again, before fire conditions threaten services and network reliability. So as we talk about requirements, we got to consider these requirements as part of the design process. And so the designer must determine what local prescriptive codes and standards require, such as NFPA 72, NFPA 90A and B, for example, and what performance-based design codes require or recommend, such as NFPA 75 and 76, as an example, and what governing gaseous suppression codes require, such as NFPA 2001. And then, of course, what do owner practices require, keeping in mind that in most instances, end-user practices will exceed prescriptive requirements. So also, is the objective to integrate with suppression? And what zoning requirements are there for actuation of suppression zones or fan shutdown? So the designer must also take into consideration the environment, such as environmental conditions. What are the cooling configurations and airflow characteristics, direction, magnitude of the area to be protected? What are the structural characteristics? In other words, what effectable parameters such as ceiling height, room geometry, equipment locations, and dimensions have on airflow patterns, ventilation, and smoke detection? External influences, could fresh air intake for cooling or makeup introduce contaminants which may affect network reliability or be the source of unwanted alarms? And of course, the consideration of accessibility once installed or for the installation. That is, for maintenance, test, and inspection within subfloor, ceiling void, above cable trays, or within fully or partially enclosed equipment cabinets, and so forth. So when designing for accessibility for an aspirating smoke detector, this means accessing the detector head itself and a benchmark test point at the end of each and every pipe run. So when properly designed, this facilitates inspection and testing per codes and standards, benchmarks performance during commission, and bring testing to an accessible location, which is one of the virtues of an aspirating detection system. A properly designed test point will be located near the finish floor, requiring no special equipment such as ladders or scaffolding to access It'll be oriented downward towards the floor and be constructed using fail-safe configurations such as a quick connect configuration as we've shown in this illustration here. A test point label located by the test point provides a convenient location to document benchmark parameters, including other useful information about the system and its installation. And finally, the designer must take what's been assessed and apply an appropriate coverage technique to effectively protect each area. Air sampling networks are designed and installed to monitor the total room for smoke concentration, not simply an area within a larger space. And this requires that air samples be continuously drawn from the ceiling, within concealed spaces, such as above ceiling and below raised floors, along air distribution paths, and within fully or partially enclosed spaces, such as containment aisles and or equipment racks and cabinets. So there are essentially 4 sampling methods for accomplishing this objective. And those are open area detection, and you'll see that there's a variety of considerations for open area. Concealed space detection, monitoring of air handling units and mechanical airflow paths, and enclosed space detection. So typically a space may use more than one method. So as we talk about below ceiling sampling, the first we'll consider is just at the ceiling, directly below the ceiling. And this method is used to sample air from areas that fall outside the direct airflow path created by air handling units, and for fire detection when the air conditioning is off. Prescriptive codes such as NFPA 72 and performance-based codes such as NFPA 75 and 76 will dictate the requirements. The method involves placing sampling ports along the pipe network, typically 1 to 4 inches from finished ceiling, facing downward. Sampling ports are spaced in compliance with sensitivity objectives for the space. So in other words, back to our acronyms here, SFD, standard fire detection at 900 square foot, early warning fire detection at 400 square foot, or very early warning fire detection at 200 square foot. So depending what the sensitivity objectives is defined for the space, you'll space the sampling ports in that configuration. Construction is typically accomplished using rigid 3/4 inch sampling pipe, supported every 5 feet, and labeled in accordance with NFPA 72. Sample holes or ports are drilled directly into the pipe network facing downward, and as we discussed earlier, a test point is generally brought down to an accessible level or location for benchmark testing. So as we're still on the subject of open areas, we have yet another configuration for area detection, and that considers obstructions. Cable trays and other surfaces present obstructions and could delay or possibly prevent smoke from reaching ceiling where area detection may ordinarily reside. So the use of high-low sample points is intended to overcome challenges with obstructions. This technique is addressed in performance-based codes such as NFPA 76, and the method involves alternating between holes drilled directly into the sampling pipe at the ceiling and remote drops with remote sampling points below cable trays and other obstructions. Spacing is in accordance with the sensitivity objectives, again, that is standard fire detection, early warning fire detection, or very early warning fire detection schemes. Construction can be as simple as a rigid stanchion from the main pipe trunk, or to facilitate relocation of remote sampling points, consider the use of flexible fire-rated tubing and use additional lengths, generally in excess of 2 feet, coiled and secured for future relocation. And of course, still on the area discussion of open areas, we have potentially beam pockets. Beam pockets are created between large ceiling beams. And depending on the size of the voids and the depth of the beams, it may be necessary to sample within each interbeam space or pocket or underside the beam in order to comply with local codes and standards. A typical on-ceiling air sampling pipe network would normally be mounted below these large areas as illustrated in the figure 2 here that we have shown below. Rigid pipe or flexible tubing with remote sampling point may extend vertically from the sampling pipe upward into the space between the beams as we've illustrated in figure 1. So sample ports are drilled directly into the pipe network facing downward towards the floor. And it's good practice to, again, incorporate a test point, as we've shown before, with this coverage technique, as generally these ceilings may be high or obstructed, and getting to the test point at the ceiling would be very difficult. So we want to bring that test point down. You'll see that kind of a common statement within each and every one of these slides or techniques. And then, again, as another configuration for open area, we may have to deal with false ceilings for aesthetic purposes, and that is, a common practice to install the pipe network of an aspirated detection system in the ceiling void with capillary tubes suspended through the ceiling tiles and into the room at locations and spacing, again, determined by the coverage and density objectives. So this is primarily so we don't see the piping below the ceiling. All we see is the remote sampling ports below the ceiling. So in this configuration, the pipe network is again installed above the ceiling, and the sampling points extend through the ceiling using either a pipe nipple and end of cap of a length of capillary tubing attached to manufacturer's supplied capillary sampling point. And again, we want to locate that sampling point 1 to 4 inches below the false ceiling, and again oriented downwards towards the finished floor. So it's important to ensure that only fire-rated tubing and fittings are used in the construction of such drops, and that the tube lengths for remote drops do not exceed that listed by the manufacturer. Capillary sampling is also beneficial for strategically locating sampling ports within enclosures, such as fully enclosed cabinets, or in partially or fully enclosed containment aisles. All right, that brings us to discussion about concealed spaces, such as raised floors and sometimes ceiling voids of IT communication facilities, which may contain large quantities of electrical cabling. In such cases, it is important these areas are protected. When used for return and supply plenums, the presence of high airflows in these concealed spaces will lead to rapid spread of fire and smoke. Aspirating smoke detectors are well suited to this task, with detectors able to be positioned outside the protected area for convenient access for service and maintenance. So this method involves placement of sampling ports within the concealed space, and again oriented downward. Where the space is used as a return or supply air plenum, orienting the ports at 30 to 45 degree downward orientation to the incoming flow will further assist to counteract pressure effects. Plus, this will prevent buildup of dust and dirt at the location of the sampling port. So sampling ports are spaced in compliance, again, with the sensitivity objectives for the space. And again, that is the standard fire detection, early warning fire detection, or very early warning fire detection scheme. And construction is typically accomplished using a rigid 3/4 inch sampling pipe supported every 5 feet and labeled in accordance with NFPA 72. So in spaces classified as plenums, we've got to ensure that all material are approved and listed for plenum use. And again, a test point is generally brought out to an accessible location. This generally means bringing that test point above finished floor for ease of access for benchmark testing and inspection. All right, brings us to the discussion about air handling unit, in this case return, supply, or exhaust grill monitoring. So the idea here is that airflow interferes with the normal dispersion of smoke. And since the rate of smoke generation in a smoldering fire is relatively small, and airflow velocity in an IT and communication facilities can be quite high, the movement of smoke is dominated by the airflow of the mechanical systems. And furthermore, smoke generated during the incipient stage is cooled by the airflow, and therefore it has very little thermal lift. And this often prevents smoke from moving directly to the ceiling, reaching ceiling detection points, causing the smoke to dissipate more widely. Well, this can be overcome by complementing area detection at the ceiling with sampling at all points where air leaves the space, such as at return air grills, transfer grills, or exhaust grills. So care must be taken to orient the sampling holes 30 to 45 degrees towards direction of the incoming airflow, and that the sampling pipe stand off between 2 to 8 inches in front of the grill, and this is in order to avoid the low pressure point directly at the grill surface. For spacing, performance-based codes such as NFPA 76 and general industry practice require a maximum area coverage per sampling hole of every 4 square foot of grill area. Constructing a pipe network generally involves use of, again, rigid 3/4 inch fire-rated pipe with sampling holes drilled directly into the pipe network, paying attention to sample hole orientation, as we discussed, and the distance off the face of the grill. And so where maintenance requires the removal of the sampling pipes on a regular basis, such as access to the filter bank within the air handling unit itself, for instance, the pipe network design should provide for the use of socket unions to permit the removal of the grill. So, a similar approach is often applied to fresh air intakes, as the fresh air coming into the building as a means to monitor incoming air, which may carry contaminants such as smoke-laden air from forest fires within the vicinity, or the occasional crop burning, should the facility be located near farmland. Pollution from populated metropolitan areas also pose a contamination risk. So by placing sample holes 30 to 45 degrees towards the incoming airflow, covering every 4 square foot of grill area, aspirating smoke detection systems can effectively monitor the incoming air from contaminants and provide logical control of dampers through the building automation system, for instance. In a fire event, ventilation duct systems can convey smoke, usually hot toxic gases and flames, from one area to another. Duct systems may also supply air to aid combustion in the fire location. Therefore, the effective management of smoke control, such as dampers and shutters to contain smoke spread and fire growth, is essential for life safety and asset protection. In-duct sampling is accomplished by installing a dedicated aspirating smoke detector and inserting specially configured 3/4 inch rigid sampling pipe and exhaust pipe into the duct, and of course carefully following manufacturer's guidelines in doing so. It's important, again, orientation of sample holes should face 30 to 45 degrees towards the incoming airflow, and where the HVAC returns are ducted and have multiple intakes, the sampling pipe may be installed in the ducts at the first common point where the duct serves the entire protected area as a means of efficiency. And on a discussion for enclosed spaces, such as in racks and cabinets, fully and partially enclosed cabinets and racks present a challenge for smoke detection outside the enclosure, as an enclosure imposes a barrier obstructing dispersion of smoke outside its confines. So there are numerous types of electrical components housed in equipment cabinets that exhibit very slowly progressing degradation before the flaming stage of fire occurs, and again, we refer to this as the incipient stage. So most electric and electronic components will degrade over a long period of time with observable telltales that can be sensed by aspirating incipient smoke detectors designed and installed to detect within the enclosure. So this method involves placement of the sampling points directly into the enclosure and positioned where smoke will collect. This may be at the top of the cabinet or perhaps side or bottom or mechanically ventilated. The orientation should be downward or, again, where the airflow is present at a 30 to 45 degree angle towards the incoming airflow. And the construction can either be rigid sampling pipe or small bore flexible tubing placed within the cabinet, positioning the sample port within the cabinet. And where there's a need to have pinpoint addressability, consider aspirating smoke detectors capable of addressing to an individual point or dedicated detector in that manner. All right, and so then we're on discussion here of containment aisles, which we also can consider as potentially an enclosed space. So, you consider high temperatures, air velocity, dilution, placement, where to place detection, and the potential for smoke spread. That is, once smoke enters the airstream, it can get transported through the plenums into other spaces or other containment aisles. So the method sample is essentially taking sample points, locating within the enclosure, and positioning them in the return airstream at collection points. The orientation is 30 to 45 degrees downwards towards the incoming flow, and the spacing depends on the configuration, since we can have a variety of different configurations, and we're always seeing new configurations. But essentially where we have open aisles, that is open entry points into the plenum, consider every 4 square foot of opening to the plenum with a sample port. And then, of course, there's chimney configurations, and which we can consider in an application very similar to what we would a duct application. But essentially, the best guidance is to follow manufacturer's guidelines, as there's many configurations that we can see in this type of space here. Construction, again, could be rigid pipe or flexible tubing, depending on the configuration. All right, so that then brings us to the discussion that, we got to have some level of equipment selection. So once site conditions are known and coverage techniques selected, the designer must identify the appropriate aspirating detector to meet the project requirements. So selection criteria should include considerations to, of course, listings and approvals, of course, optical integrity. Consider longevity of the detector and its ability to maintain absolute sensitivity thresholds throughout its operation without the need for recalibration, baselining, or drift compensation techniques, all which can compromise performance objectives of the system. Consider sensitivity range for staged response throughout all stages of the fire growth and the reliable release of suppression. Consider its compatibility with other systems and coverage capacity. So selecting appropriately sized detector that best suits the coverage area or object being protected, ensuring efficiencies are achieved. And otherwise, we unnecessarily burden the project cost and take up valuable real estate and contribute to increased maintenance cost. So as an example, a perfect example would be selecting a detector rated for up to 8,000 square feet, for instance, and applying it in an area or object that could have been served with a 2,500 square foot rated detector. So on the flip side, imagine applying multiple 8,000 square foot detectors to serve an area that could have been served with a single 20,000 square foot detector. So it's important to size the detector for the application to achieve certain efficiencies. So along that discussion, consider advantages of a multi-pipe system versus a single pipe system. So subject to maximum length parameters for the detector, it is possible to design a pipe network covering an entire zone with one pipe. However, for improved pipe network efficiency, it is strongly recommended to use shorter multiple pipes. So the advantages of multiple pipe systems are shorter pipes have better response times as the air transport distance from the end of the pipe to the detector is reduced. Shorter pipes have less sampling holes per pipe and can have smaller end cap holes. This creates better hole share and hole balance. And shorter pipe lengths are likely to have fewer bends, resulting in shorter transport times and better airflow. And of course, as a consideration of system balance, multiple pipes provide better system balance. You also got to consider pipe and fittings, which form an integral part of an aspirating smoke detection system. So consideration must be given to type of material, ensuring material selected is fit for purpose and approved for use by local building codes, has low flame smoke spread. When used in plenum spaces, is plenum rated dry and listed with the detector, and it's labeled in accordance with codes and standards such as NFPA 72, uses appropriately listed fasteners, and can be sealed and permanently fixed in accordance with codes and standards, again, such as NFPA 72. Consideration must also be given to remote ancillary items, which can contribute to the efficiency of installation and effectiveness of operation by placing components, where needed, for the ability to view status, program functions, and manage all aspects of the system remotely. This includes the use of remote displays, programmers, potentially remote relays, putting the relays where most appropriately or conveniently can tie into other systems, and of course the use of remote management software to manage and control the system. So IT and communication centers, this now brings us to the coverage area discussion that we'll have here, but IT and communication centers are comprised of many interdependent adjacencies. each contribute to the operational continuity of the facility. An event in any part of the facility can affect uptime objectives. It's good design to consider a holistic approach with multiple sampling locations throughout the facility, typically using multiple coverage techniques, some of those techniques that we discussed earlier. So let's look at it by area. As we look at and start with the data hall, we'll consider placement of sampling points within concealed spaces housing combustibles, such as above false ceilings or below raised floors, in enclosed spaces, such as within containment aisles or at the point where air leaves the enclosure, within open areas below the ceiling, at return or supply side of air handling units. In switchgear rooms, consider placement of sampling points within the switchgear enclosures themselves and within open areas below the ceiling. Similarly, in electrical distribution rooms, consider placement of sampling points within distribution panel enclosures, within open areas below the ceiling, and within concealed spaces housing combustibles such as false ceilings or below raised floors where present. In battery rooms, consider placement of sampling points within open areas below the ceiling and in concealed spaces such as above false ceilings where present, and also consider monitoring the area for off-gassing of hydrogen. And in generator rooms, consider placement of sampling points within electrical enclosures and within open areas below the ceiling. And in the chiller plant, consider placement of sampling points within electrical enclosures and within open areas below the ceiling. And in CRAW galleries, consider placement of sampling points within concealed spaces housing combustibles, such as above false ceilings or below raised floors where present, within open areas below the ceiling, and at return or supply side of the air handling units. In intake structures or penthouses, consider placement of sampling points within the path of the incoming airstream, again with the intent of detecting the outside environment, which we can consider as an adjacency, which could lend itself to bringing in contaminants through the rest of the facility, and we want to monitor this point. And so a good method is, again, to monitor the incoming airstream in these spaces. In modular structures, consider placement of sampling points within concealed spaces housing combustibles, such as above false ceilings or below raised floors where present, within open areas below the ceiling, at return side of air handling units, within enclosures such as fully, partially enclosed server racks and or control compartments where present. Also consider monitoring area for hydrogen off-gassing where battery storage is internal to the space. So no system would be complete without tie-in to other systems for signaling of alarms, reporting, and management of the installation. Multiple paths are possible, and the method of tie-in largely depends on the capability of other systems. So advanced aspirating smoke detectors can provide connectivity through relays, intelligent interfaces with OEM equipment, through open protocols for more customized level of reporting, or through manufacturer-provided system management and control software for management of a single or multiple networks, either on-site or remotely anywhere in the world. So integration paths include connectivity to, of course, fire alarm control panels, and this may be via relays or listed intelligent high-level interfaces. With suppression control panels, similarly, via relays or listed intelligent high-level interfaces. And where we're interfacing to building automation systems, this may be via relays or intelligent open protocols, or, in the case of a national or regional operations center, via relays tied directly into the alarm block through intelligent open protocols or through manufacturer-provided system management and control software. So, in closing, Fire detection systems play an essential role in the overall fire protection strategy and are critical for mitigating risks. Dynamic environmental and operational characteristics of IT communication facilities have resulted in a shift towards performance-based approaches, applying detection-specific environmental and operational conditions to meet particular facility requirements and owner objectives. Aspirating detection systems are well suited in meeting performance objectives of modern IT and communication facilities with proven applications worldwide. Designing an effective solution takes into consideration coverage objectives, requirements, and the environment. Multiple coverage techniques are possible, and generally a space will use more than one method for an effective level of protection. Selection of equipment is crucial. Careful consideration must be given to selection of the detector, pipe and fittings, and ancillary items needed to form an effective system capable of meeting all performance objectives and efficiency requirements. For the selection of coverage areas, we must look at each facility holistically, taking into consideration interdependent adjacencies that could affect reliability and uptime objectives should an event occur. Common coverage techniques are deployed, and a space will generally require more than one method, as we discussed. Multiple communication paths with other systems is possible for signaling of alarms, reporting and management of an installation. The choice depends on project and owner requirements, compatibility with other systems, and the need for intelligent analytical data. So with that, I close and I hand the floor back over to Morgan. Thank you.
Excellent, Steve. Nice job. Say a few of you have already submitted questions, so we're going to go ahead and jump right in while the presenters answer your questions. You can take this time to answer the event survey, which can be accessed by the red icon in the widget bar at the bottom of your screen. Also, just a reminder that to receive continuing education credit, you must attend the entire webinar, and the Q&A is included as part of the webinar. So anyway, first question. This has to do with what information, Steve, do you need from the specifying engineer when they're designing an aspirating type smoke detection system for application like you've described here? I mean, you've touched on a number of elements like standard fire detection, EWFD, VEWFD, and so forth. What information do you really want to have from the specifying engineer?
Yeah, generally, we'll want, of course, the areas to be covered and what the sensitivity objectives for that area are, or discussion about coming to some agreement as to what those sensitivity objectives should be. And so, we start with that, and we also, generally would like to know what the ventilation schemes are, what the mechanical systems configuration are for the space. What zoning requirements are there, such as what fans need to shut down, or what addressability needs to occur in terms of zoning for, say, suppression zones. So that's equally important. And then also, getting down to some fine detail in terms of where we can put equipment, which lends itself to deciding which equipment we select and length of pipe, and any special configurations that we have to do to the pipe to make the most efficient use of the design to achieve the best response time and so forth. So the critical things are, of course, what areas and what the sensitivity scheme needs to be. Are we doing an NFPA 72 compliant prescriptive measure with placement just at the ceiling? Are we doing a very early warning scheme which considers detection at the ceiling and at return air paths and so forth? And what compartments are there, and what concealed spaces are there? So I hope that helps a little. I know it's across the board there, but
sure, it was a very broad question. Similar to that question, you talked about some guidelines for SFD and early warning fire detection, very early warning fire detection in terms of coverage areas, 200 square feet up to 900 square feet. And you also, at the beginning of your presentation, you alluded to kind of performance-based design. I mean, would it be possible for the specifying engineer to kind of tailor that based on the hazard that they anticipate, or put another way, I mean, those are broad rules of thumb that you've articulated. They're probably based on experience, but would it be possible to kind of engineer that a little bit?
Yeah, so if I understand the question, I believe the question is, what criteria decides as to the decision to use SFD or very early warning fire detection scheme, correct?
Well, more specifically, the coverage area per, I guess it's the detector port. That's the way I understand it. Does that make sense?
I think so. The coverage area for the detector port, obviously we size the detector based on the area being covered and the application being covered. So, for return air grills, it's very easy. For instance, we know every 4 square foot of grill area, and then we just basically take the number of grills, the size of the grills, and the capacity of the detector to determine which detector and the application of the product in that fashion. For open areas, we consider the square footage of the area, the sampling density in terms of port placement, 200 square foot, 400, which will dictate, ultimately the sensitivity requirements for the detector, the capacity of the detector, which will ultimately lead to the selection of the detector. I hope I answered that question appropriately. I'm not sure if I completely understood the question.
Well, we'll see. We'll see what comes in as follow-up.
Sure.
So, this one's probably a pretty easy one. You talked about when placing the detection ports in ductwork, having those basically installed at 30 to 45 degrees. Is that measured from the horizontal or the vertical?
That's measured from the horizontal, or the incoming direction of the airflow. If maybe a better way to state that. So we want to consider the direction of the airflow, and we want to face the airflow within a 35 to 45 degree, but generally downward towards the incoming airflow, if you know what I mean.
Okay, perfect. And there was a related question that had to do with locating piping in a plenum space or duct. There are limits on, kind of things like flame spread, smoke developed on, when non-metallic materials are used in ductwork or plenums. Are there any restrictions on sampling piping when installed in those kind of spaces?
Yes, again, as my comment was, that you want to use plenum-rated piping that's listed with a detector dry. So generally we'll use CPVC, which has a low flame and smoke spread and is plenum-rated with certain manufacturers' detectors plenum-rated dry. I mean, you'll see CPVC used in residential sprinkling, for instance, and it's listed wet, but where it's listed with the detector is generally listed dry. But that material is UL listed for plenum spaces.
Okay, excellent, thanks. There's a couple folks asked this question. You, during your presentation, talked about multi-pipe systems where you had a couple illustrations where basically you showed how you could protect a single space with 1 pipe run, 2 pipe runs, even 4 pipe runs, and there obviously the trade-off is one of basically increased precision of where the alarm from where the alarm condition arises, right? More pipes presumably gives you a little more precision there. Yep, that's the slide there. So I guess one question was if there are any real limitations on the length of sampling pipe that could be used in a single run.
Well, it's defined by the capacity of the detector. I mean, various detectors, again, depending on manufacturer, certain manufacturers have detector ranges that go from small area to large area, which in fact, affect the length of pipe or the capacity of pipe for that system. So, you take a large area detector that has the potential of multiple pipes, and the idea of using that all 4 pipes in such a manner that you break up a much larger space into smaller quadrants per pipe, and the capacity of the pipe depends on the capacity of the detector. And so without noting a very specific, manufacturer's guidelines in terms of maximum pipe, but it comes down to the capacity of the detector and what the overall pipe length can be for that given detector.
Okay, great. This seems to be a follow-up to the question as to kind of spacing areas, as it were, which is the questioner says, I suspect that the previous question had to do with the requirement to derate spacing based on air velocity. If you look in NFPA 72, there's guidelines where there's higher airflows, and do ASD systems have to basically reduce the spacing based on airflows like spot detectors would?
Yeah, so if you look at that table in NFPA 72, it suggests the derating factor based on the airflow or air change rate. And in the case of aspirating detection systems, and it also knows beam detection, that refer to manufacturer's guidelines. And so, it has the exclusion, and in that respect refers to the manufacturer's guidelines. And, certain manufacturers will have different philosophies. We, for instance, will suggest that no derating needs to occur because it is an active system. It's actively drawing the environment, and we're derating spacing based on sensitivity objectives, not necessarily its ability to perform in a given air velocity or magnitude of airflow. So the answer would be no, we're not derating. So if we're doing very early warning fire detection, the air velocities are in excess of 60 air changes, we're still going to be at 200 square foot as defined in NFPA 76 for very early warning fire detection systems.
Okay, great, thanks. So a question has to do with inspection, testing, and maintenance. Attendee asks, how and when should the sampling pipe be cleaned or serviced?
All right, so that's a question that really depends on the environment, and we'll see that most IT and communication infrastructures, the very seldom or very rarely see that the pipe needs to be cleaned, but there are provisions that, in the event that you do need to clean the pipe, and there are some, monitoring points within the system that monitor and supervise for flow. But quite frankly, as you're doing your benchmark test, and the fact is, annual inspection is required of fire detection systems, including aspirating detection systems, or owners may have other requirements that exceed that requirement. But the idea then is that, as you benchmark test and you see that there's flow differentials from what the benchmark test commissioning to your annual test that might dictate cleaning the pipe. With an air sampling detection system, it's very easy, and the process is essentially back flushing the pipe network, using, say, a vacuum at one end of the pipe, and generally disconnecting the pipe from the inlet of the detector when you're doing that process. So it's a very simple process, and in that whole process you're cleaning the entire pipe network without having to physically get to each and every individual hole. I hope that answers that question.
Great. So here's a specific question that came in from one of the attendees that they ask, if a raised floor is used as an air plenum, common with the open area above, what would drive the need for detection points in the concealed space, that being under the raised floor, if the open space has adequate detection?
I'm sorry, so repeat that question.
It sounds like if you have a space that has a raised floor that's being used as a plenum, what would drive you to put detection ports in both that plenum space or underneath the raised floor in addition to in the protected space?
Well, generally, if you have combustibles, what might drive you to that is codes and standards requirements. But generally, if you have combustibles in the raised floor, or in the event that you have suppression, say gaseous suppression or pre-action systems below the raised floor, but more specifically pre-action systems, gaseous suppression systems, thinks in terms of the requirement for needing detection to actuate those systems. So it comes down largely to the presence of combustibles and the need to initiate suppression systems that may be located below the raised floor.
Okay. You had a slide in your presentation that talked about integration with other systems, and one of the attendees has asked if there are Modbus and BACnet gateway connections for the BMS available.
Right.
Does that make sense?
Let's see if I understand that question here. So the question was, can air sampling detection technologies interface with Modbus or BACnet?
Yeah, I think that's what the question asked, and if there are specific gateway connections available.
Yeah, so essentially, different models and different manufacturers have different communication methods for Modbus and BACnets. I mean, there are various models of detectors on the market that do have that capability, and then there are third-party interfaces, or black boxes, if you would, that are available in the market that will take the open protocol from various manufacturers' panels or detectors, and bring them into their black box where they'll do the Modbus BACnet conversion. So that is available, and we can be specific for particular individuals interested in knowing what those third-party units are available.
Sure. Here's a specific question. Sounds like the person asking this question specifies this type of system frequently. They ask, how many computer room air handlers can realistically be covered by a single pipe on a multi-pipe detection design? It says manufacturers seem to recommend one pipe per air handler, but they've heard of instances of up to 4 units being covered by a single pipe. Does that make sense?
Yeah, it does, and it depends largely on the velocity of air going through the air handling, the size of the air handling unit, the size of the grill. The idea is just really important, to take a single pipe across multiple air handling units. You're then taking sampling ports and extending them from one air handling unit to the next. Now, if you've got air handling units cycling, where you have one that has more velocity and more pressure, if you would, than the other, you could actually create a Venturi effect. So the challenge is that you could force smoke the opposite direction if you're taking holes from one pipe. Normally, it's recommended that in that case where you're monitoring multiple air handling units off a single pipe, to branch the pipe and have individual branches, so you're not creating that Venturi effect with holes going across one air handling unit and on, to the next one, if you would. So that's very important. And also consider dilution. The more air handling units that you're monitoring, the more dilution that you're introducing, and the larger the fire growth may be by the time it detects, depending on how much dilution is actually being introduced into the system. So good practice is generally one pipe per air handling unit for the average size air handling unit. Where smaller air handling units are used, the idea of doing multiple air handling units, and I won't say how many because it all depends on the size and capacity of the air handling unit, but it is possible to use a branched configuration in a single pipe to get multiple air handling units. I would say discuss with the manufacturer for very specific application.
Great, thanks. Another question, for those who use NFPA 72 frequently, we're well aware of, the changes that have occurred over the last couple editions that have to do with things like beam pockets, waffle ceilings, and so forth. And you addressed those briefly in your presentation. Then one of the presenters asked whether sampling points need to be located within 4 inches of a ceiling where solid beams exist throughout the area, or can those sampling points be located at the bottoms of the beams as allowed by NFPA 72 for spot detectors?
Right. So as you'll see in this slide here that we address both configurations where sample points are directly, below the beam pocket, and it's considered, a flush ceiling in that respect. But it comes down to what the local jurisdiction will accept, and also what combustibles are in the pocket. And so, this configuration that we show in Figure 2 here on the screen considers that there's no combustibles in the pocket, and the local jurisdiction will accept that. And that's what it generally comes down to. In the event that you do have to get up to individual pockets, whether because of the local ASJ or there are combustibles, it's a matter of just using a T and a 90 to bring a sample point, kind of like a walking stick, if you would, configuration up into the pocket.
Okay, great. Thanks.
We actually have a white paper. I mean, there's additional resources, I guess, by within the industry on the subject, and it goes in much greater detail. That can be used to help support the application of just below the beams for various AHJs that may have, concern or questions as to applying it in that fashion.
Okay, last question. You talked about basically configurations with suppression systems, and one of our attendees has asked whether Xtralis systems have been installed in conjunction with fixed aerosol suppression systems.
Yeah, I can't say for certain. We have many channels in which we distribute our products through, and that the products are actually applied through, that we don't know very specifically, all the various gases or aerosol suppression systems that may have been interfaced with. The fact is it's capable of interfacing with any magnitude of suppression system. It has a threshold designed such that when programmed appropriately, it can be used very reliably for the release of suppression. So which suppression agent is it releasing? That's not something that we really dictate, for that matter. I hope
Sure.
that answers the question.
Designer's prerogative, I guess.
Yeah, that's correct. Right.
Okay, well, I'm afraid that we have run out of time. So on behalf of the Society of Fire Protection Engineers, I'd like to thank Xtralis for making today's event possible, and I'd also like to thank everybody for joining the webcast today. I'd like to wish everybody a productive remainder of their day. Thanks again.
Thank you.
Ladies and gentlemen, this concludes today's call. You may now disconnect.